Hey there, I'm Nix, and today's video we're continuing on with easing you through how to get started on the LeetCode website if you're brand new to it and you're still in the process of learning some foundations of coding. In this video we'll solve a problem two different ways, and of course I'll give you all of the details of the entire process, through the planning of the algorithm, to the coding of it, to the analysis of time and space complexities. If that sounds interesting to you, then stay tuned. Welcome back. Now, as in the last video, the thing we want to do is use this acceptance rating to find our easy to solve problems for easing ourselves into how LeetCode works and to start building up our LeetCode solving prowess. So last time we did build array from permutation. The next apparently on the list is the concatenation of an array. Now that the page is loaded, we are given an integer array nums of length n. We want to create an array answer that has twice that length, 2n, where the answer at the index is exactly equal to the answer at that same index in the nums array. And answer I plus n, so the first position in the new doubled length section, is also equal to nums I. So basically we're going to repeat all of the integers in the nums array twice. Zero index, specifically answer is a concatenation of two nums arrays. Exactly. So as we see here in example 1, if nums is an array that has 1, 2, and 1 present in it, then our output should be an array that has 1, 2, 1, and then 1, 2, 1 again. As I stated before, we're going to do two slightly different ways of solving this problem to show some advantages and disadvantages of certain ways of tackling it. The first way that comes to mind is, well, if we want to create an array called answer, let's actually create an array called answer. When we have that new array, we can then loop through our nums array and then add two things. Add what the answer at position I is equal to, and then add what I plus n position is equal to. So these two things will be our code within the for loop. Then after that for loop has occurred, we'll just return answer. So let's take a look at that code. First up are variables. Technically, I don't need this first one where I have an integer variable that I call n just to keep in line with what the problem calls things. Technically, when I make variables, I tend to want to give them more descriptive names. So here I would probably name it size or something. But again, I want to keep it in line with what is being called here. Technically, I don't need to do that because whenever I use n, I could just say num size, but it makes it a little cleaner when reading through the code. So I took the option to go ahead and create it. Now with this, I'm going to create a vector of integers to serve as our quote-unquote array, and named it answer. I've also pre-allocated the space to be 2 times n. Now I have a for loop here, and like I said, the for loop goes from the beginning of the array all the way to the end of the array and increments up by 1, and we just use these two pieces of information as our code. We want answer value at position I to be equal to the nums at the same position, and we want to have answer I plus n be equal to nums I as well. Then after that, we make sure to return our answer because this method expects a vector of integers to be returned. And that should be all that is needed to complete this problem. So let's start pushing buttons and see if I've messed anything up. Okay, 1, 2, 1, 1, 2, 1, lots of 1, 2, 1s. This looks good. Let's go ahead and do the full submission and see if I get another acceptance. Great, I didn't mess anything up. Lovely. Now, it gives us a hint as to where our rankings are, but first, before we go ahead and look at the graphs, I want to analyze the big O complexities here. For space complexity, we have a vector of integers that we created, and this variable in terms of its size is dependent on what the size of our original nums array is. The bigger the nums array, the bigger this vector is going to be. At the for loop we do constant work, so really this is what is dictating our space complexity, and because it's linearly dependent on the size of the nums array, we have a big O of n space complexity. For time complexity, looking at this for loop here, we're only doing constant work within it, so how much time we take is going to depend on how many iterations this for loop does. And it's going to go until, again, we go through the size of the nums array. So because it's also dependent on that, we have linear time complexity, big O of n there as well. Let's go ahead and click on the accepted text to bring up the ranking graphs here, and we're right in the middle of time. This is pretty much a skewed bell distribution, but I'd expect to be able to ping pong around here. Looking at memory, we have a pretty good ranking. Again, I'd expect maybe a little bit of ping-pongings. And again, just like I showed you last time, if you're curious, you can click on any of these columns to see representations of solutions that belong in each of those slots. So it's an excellent way to learn different ways of being able to tackle problems. Now going back here, there is a slightly different way of performing the same kind of actions. Instead of making an answer vector, we could continue with our nums array and use the pushback method. That may have also popped into your mind as a way to solve the problem. So let's look at what that code would look like. First up, I get rid of the answer vector. I don't need it. And instead of these lines, this will also go away, and what we want to return ultimately is going to be nums. So now I just have to figure out what goes in the for loop. And as I mentioned before, we're going to use pushback. So to do that, we call the nums array dot pushback and tell it what we want to push back, which in this case is just nums I. So this will add on a repeat of all of the values that are already in nums. Now testing this code, we should get the same thing. Yep. In submission, barring me messing anything up, okay, we also get an accepted ranking. Now looking into the big O usage of this solution, well, it may appear, because we don't have that vector up here to store our answer, you might think our memory usage is less, but that's not really the case. That's not necessarily the case. The reason for that is how the pushback works in certain situations. Take this example here. If our nums array has 3 things in it, so its size is 3, and let's imagine that its capacity, its total possible storage space, how many things you can cram into it, is also 3. Well, when you call the pushback function, it's going to see that this array doesn't have any more space to fit anything in it. So what it's going to do is it's going to create a new array, move or copy over the old things in it, and in this one, it's going to have more capacity. So now it does have room to push back another value, in this case, 1. And depending on how the implementation of pushback works, how much extra capacity, extra storage space it puts will vary a little bit. If it doubles the size of the capacity, and that's exactly what we want, great. But let's imagine instead of this example, we have, say, this example, where our num size is still 3, we have 3 things in it, but let's say the capacity for this array is at 5. It could fit 2 more things in it. So when pushback is called, it sees it has enough room to add 1, and it sees it has enough room to add 2. But now when it tries to add the final thing, it's run out of room. What is it going to do? It's going to carve out space to create a new array with more storage space. And let's say it, just like the last time, it doubles the capacity. Well, in this scenario, we go from an array with a capacity space of 5 to a capacity space of 10. But we only need to have 1 more thing in it. So we could potentially carve out an array that takes up some more space than we need. Finally, a third example here that I want to go over let's say we have this array, and let's say the implementation of pushback, when it sees it doesn't have any room, it creates this array right here. The amount of extra storage that it gives the array can vary depending on the implementations. Usually it's at least 1.5 times. It could be 2 times, but it usually falls somewhere within that range. But if it is this kind of implementation, where it only really creates 1.5 times the space, then we're going to create this array. After everything is moved, we have the values here, and pushback can add some values. It adds 1, it adds 2, and it has run into the same thing again, where it doesn't have enough space to add everything, so it needs to create another array, carve out some more space, and so on and so forth. So as you can see with those examples, pushback may carve out space and thus use up more memory than we technically need. It could also, depending on its implementation, need to carve out and create new arrays and then eliminate the old ones more than once. So those situations are drawbacks of the pushback function, and each of those take up memory. And this would have a higher linear dependence on the memory, thus higher memory usage. That also comes into play in the time complexity as well. In the cases where pushback can just immediately add things, it's a constant amount of effort. So say big O of 1. If it's always big O of 1, then again we just depend on how many iterations of a for loop, and it will have big O of n. But whenever it reaches those scenarios where it has to carve out space for a new array and move things and copy things, all of that takes more time. And all of that also has linear dependency. So occasionally it's going to run into some work where it has linear dependence here and linear dependence here, so it won't be quite as fast as the previous answer as well. Now looking at the rankings, we can see the evidence of that. In this instance, we have a lower runtime, although I'd expect it to be able to ping-pong around. And in memory usage, you can see we are much further down here, and that's because of the pushback's occasional increased memory usage for this type of problem. So for me, I'd prefer the first solution I showed, and I have a tendency to, if I can avoid using pushback, then I'll try to do so. Pushback is great if you don't know how much memory you're ultimately going to need to carve out, but in this case with this problem, we did. We knew our final answer was going to be exactly twice as big. So knowing that, it's really easy to carve out exactly that memory usage for it. Alright, that was the concatenation of array problem on the LeetCode website. I hope this video helped you out in some way. If it did, consider subscribing. And as always, I will wish you happy coding and to have a nice day.